你要在任何一个事情，它都包含但是我没有想到，我觉得他把我卡到T 后面相同，我觉得我昨天卡到T，然后我想明白，
不应该卡在 T 上。行，我把我猜真错了，想怎么贴近一下它的代替。跟 T 之前最后的区别。你越想越看，我在想什么？这个是非常好的一个事情。我们是搞 Q 的，不一样。
这不是，我有神助。
哦，懂了。不是，神不搞叉吗？
还是搞只要是我有洗澡的小舞台，
是。神还是学比我好。本来他这个人品，他是属于这样。
Good morning, everyone. So let's continue our discussion on the randomized block coordinate descent method. So here's a recap of the definition we mentioned in the end of last lecture. This is the total expectation of phi of xk. And so this is called phi k, and for the total expectation of epsilon of xk, it's epsilon bar k. And the difference between this expected value and the optimal solution, the optimal value is delta k, and the inverse is called tau k. Previously, we had three key lemmas. These two, so suppose x0 is given, so fix all the randomness embedded in x0, and then we do one iteration of the randomized block coordinate descent method. This is the conditional expectation, right? Conditional on all the previous randomness. And so this is the inequality we have. Basically, we can view this as an upper bound on the sharp norm of R. And this lemma gives you the other side, the lower bound of the norm. And this is also using the same notation as before. X0 is given, and the epsilon I is also the epsilon of xi for the current iteration. So all the previous randomness has been fixed. The last lemma we mentioned last time was this iteration difference, right? So phi k minus phi k plus 1 is lower bounded by epsilon k plus 1 bar. And also, if you subtract 5 star here and subtract 5 star here, then you can also have this difference between the delta function value. Okay, so that's all the key lemmas we had last time. Okay, so far we haven't specified what the PMF is, right? And now let's focus on the simple case when all the PIs are just 1 over B. It is a uniform distribution. Okay, so in this case, let's make this observation. Basically, what we wrote here is the numerator here. But suppose your x0 is actually at iteration k, so this is xk, and this epsilon I is actually epsilon of the next iteration, right? This is the random output xk plus 1 where you update i's coordinate, so it's called epsilon I. This is the notation we introduced last time. So let's consider this quantity here and write it in terms of an expectation. So going from this side, because PIs are just 1 over B, so the two summations are the same. And from here to here, we just rewrite this summation as an expectation, as a conditional expectation, right? And now we discuss two cases. The two cases are based on the relationship between these two quantities, whether this is less than or equal to or greater than 2b times this expectation. Here is just the 2 times this quantity. Okay, so this is an conditional expectation expression, right? Here the CK is fixed. Right? Remember, CK is a sequence of all the IKs before. Right, so here we assume CK is fixed, so XK is a fixed number, or it's a deterministic number to us. No randomness here, right? but indeed this one is a random number, and the randomness is in CK. So now let's take a total expectation. Okay, so here we take the expectation in CK and so here we just have expectation of this quantity in terms of CK, and here because we have one more random variable, so we have CK plus 1, and by definition this is phi k minus phi star, which is delta k, and here on the right hand side this is by definition epsilon bar k plus 1. Right, so we simplify this condition in total expectation. And so this is the key result in this case. Basically, we have this geometric decreasing sequence. So delta k plus 1, comparing delta k plus 1 and delta k, this is decreasing with the rate C1. And also you can represent this one in terms of delta K. C1 is a number smaller than 1. Okay, we're simply combining these two conditions, the star and the double star. So double star gives us the first inequality, and star gives us the second inequality. Right. So real random terms, we arrive at these two results. Right. So simple algebra. And now let's see the second case. And so for the second case, the key result we have is this difference between tau k and tau k plus 1. So tau k, so it's a similar result as before. We just need to show some kind of distance difference between tau k and tau k plus 1. In the first case, we show, so basically here we show tau k plus 1 is greater than or equal to 1 over C1 times tau k. And 1 over C1 is greater than 1, right? So here we have a relation that tau k plus 1 is greater than tau k, but we can say something more specific with this coefficient here. Well, here we show tau k plus 1 is also greater than or equal to tau k, but here it's this is additive, this is multiplicative difference, right? But we can, in both cases, we can show a specific difference between them. Here is a coefficient 1 over C1, here is a coefficient 1 over C. And here C is like a distance notion. C is defined as 4 times R squared, R is this quantity here. And in the uniform distribution case, this dual norm can be written explicitly as this form. Okay.
What is Li?
Li is the Lipschitz constant for the ice block. Right, this is convex smooth and it's blockwise smooth. Right. This result is the most involved one. So we begin from combining these two results. Right. This one gives you an upper bound. This gives you a lower bound. So combining the two, we have this result. And then, well, this is for any iteration, right? This x0 can be any iteration. So suppose we are at the kth iteration, let x0 be xk, then we can rewrite this inequality as the first inequality here, right? And from this inequality to this one, we are using the assumption for this case. Right? This quantity, this difference is at least 2 times this one. So, right, so we can upper bound this one by 1/2 this one, right? So rewriting the inequality, we have this result here. We have a 4 here. And here, from here to here, it's by the definition of the C. C is the maximum of this quantity. Right, so this is less than or equal to C. So we have the final inequality here. Okay. And then, as what we did before, this is more like a conditional expectation result. We need to take the full expectation. right? So we take the full expectation. For the left-hand side, we just use the definition. This is phi k. So expectation of this one with respect to ck. This is phi k. This is phi k plus 1. And epsilon term becomes epsilon bar k plus 1. And here we just take the full expectation of this one, right? Expectation of c. The square is inside of the expectation. So from here to here, we use the Jensen's inequality. Okay? So we can put the expectation inside the square, right? Then this becomes phi k by definition. Because this epsilon is always negative, so we can throw it away, right? And here we subtract phi star in both terms. Then it becomes phi delta k minus delta k plus 1. And here, this is exactly delta k. Okay, so here's delta k squared over c. Now we can represent this inequality purely in terms of delta k. Right? This is a recursive formula for delta k. And if you still remember, but I guess this is probably not, this is quite similar to what we have seen in probably the first algorithm, the gradient descent. Yes, yeah. So this is like the same inequality. So we can use a quite similar trick to invert this inequality and work with the inverse delta k. That's why we need to define the tau k, because working with the inverse is quite easier. So now let's invert this one. We got so this is just by calculation. And from here to here, we use the monotonicity of delta k, right? And from here to here, we just use this inequality. Okay? And this is exactly what we want. This is tau k plus 1 minus tau k greater than or equal to 1 over c. Okay, and this concludes our proposition. This is the key result for the first case. This is a key result for the second case. Now we need to combine them together to show the final convergence result. Before that, let's define some important notions for the indices. here we consider all the indices between 0 to k minus 1. So for the first little k iterations, we divide this index set into, we divide it into two. So k plus and k minus. For k plus, it means this is the second case, right? For k minus, this means we are in the first case. Right, this is case 2. This is case 1 because this, if you take full expectation for this one, we have this is exactly the case 1, and this is for case 2. So this is the final result we have for the convergence. Delta k is expectation, you can see k 5xk minus phi star. So this is the optimality gap in terms of, this is optimality gap under expectation, under the total expectation, right? So we can show, finally we show convergence in function value convergence in expectation at the rate of 1 over k. Okay, that's the result. So here we are using both the case 1 and case 2 results. Combining them together, we can represent this difference tau k minus tau 0 as the summation over the case 2 and the summation over case 1, right? So here we just split the set into 2, and this is equal to the summation in case 1 and case 2. For case 1, the cardinality of the set is this cardinality of capital K plus. For case 2, the number of indices here is cardinality of K minus. Right, and for the first one, we have, this is for case 2. For case 2, we know this difference is always lower bounded by 1 over C. Right, so we have this 1 over C. And for this one, we have, so here we have tau K plus 1. For case 1, we're now go to 1 over C1 tau K. So tau K plus 1 minus tau K. Right, because of the monotonicity of tau K, so we can always express this difference in terms of tau 0. Right? And this holds for any index in the set K minus. So we can lower bound this one always by this uniform bound. Okay? And now let's choose the minimum between the two. So we can always bound it by this one. And recall the sum of the two is just the little k, the number of iterations you have. And we call C prime as this max, which is also equal to the mean of the two. You can check they are equivalent at the definition of C1 and C. They are the same. So this is just lower bounded by K over C prime. Okay. So finally we have 1 over delta K is tau K. Right, so in the end we have, using the definition, tau K is 1 over delta K, and this inequality, we have it is lower bounded by K over C prime because tau 0 is always non-negative. And if you invert this, you get the final conclusion, the convergence in expectation. Another thing we need to note is that this inequality, the criterion for case 1 or case 2, is what you don't need to know in your implementation. This is only needed for the analysis, right? Because you don't know this delta K, delta J. It involves the total expectation and also this phi star. So this is not computable. But this is only needed in analysis. Okay, so far, what we discussed is for the uniform distribution. This is the final result for uniform distribution. You can show similar results for the arbitrary distribution. Here, without loss of generality, we assume that P1 is less than or equal to P2 and less than or equal to PB. And this is, all of them are strictly between 0 and 1. So this is the observation we make, which is similar to the case that we differentiate case 1 and case 2 in the uniform case. So based on this observation, we divide the iterates into case 1 and case 2 based on this inequality. In the uniform case, we just replace this B1 by 1 over B. So it's 2B times this expectation. But here we just use P1. P1 is the smallest probability. The key result for case 1 is the following. Tau k plus 1 is less than or equal to C2 tau k, and if you invert this inequality, you have this relation for tau k. Sorry, this is delta k. This is for tau k and tau k plus 1. Here C2 is quite similar to what we had for the uniform distribution, where we had C1 is 1 minus 1 over 2b. This is P1. But here we just replace this 1 over b by P1. I will skip the proof. It's quite similar to the case in uniform distribution. So for case 2, we just have the other case. The result for case 2 is the same as before. C is the same quantity as in the proposition for case 2 in the uniform case. So this proposition is the same. Only this one is different. We change 1 over P to P1. Okay, so as you can imagine, here we just change B to be 1 over P1. Okay, so this is the final result for the arbitrary distribution. And so the convergence rate is, again, 1 over k. Some interesting arbitrary distribution would be as follows. So usually people choose pi to be alpha I to the power alpha divided and then regularize it and normalize. Okay, so this alpha is something greater than or equal to 0. If alpha is 0, then we get a uniform distribution, right? Oh, sorry, I didn't mention what SI is. SI is just to normalize this distribution. It's just the summation of Li alpha. No SI, just S. Call it S alpha. Okay, so this is just the normalizing constant. Right? Summation of pi is just 1. If alpha is 0, then pi becomes 1 over b. Right? This is the uniform distribution. And for example, if alpha is 1, then pi is just the Li divided by summation of Li. And in the algorithm, if we choose lambda I to be just 1 over Li, as in usually in the gradient type method, we just choose 1 over the smoothness. Then the norms we defined, right, this sharp norm, this can be explicitly written as the following one. And also we can write down the formula for the do norm.
So the SI in that first norm, is that S alpha?
Yeah, S alpha.
Perhaps obvious, but so when we how is there any standard to define the dual norm? Like how to derive the dual norm? Like we need to compose to identity norm or something?
The do norm S. I don't remember wrong, this should be the definition for the do norm.
Okay, right.
I have a question related to the the door norm you wrote last time when we discussed the uniform distribution. It is equivalent to 2b, and then the same thing. We replace S alpha by b, and that's what you wrote just now.
In the uniform case, yeah, this is 2b.
Yeah, so why is 2b?
What I wrote last time is different?
Yeah, it's 2b. Yeah, it's 2b. Yeah.
No, what I wrote last time is different from this one? Or
I mean, why? So here you mean S alpha equals to b, right?
S alpha, yeah, it's equal to b. because if
Oh,
in the uniform case alpha is 0, this is just a summation of ones.
oh,
Right. This is
oh, okay, okay.
summation of 1,
Oh, okay.
so it's B. Okay, so then this finishes the discussion on the randomized coordinate, broad coordinate descent method. But we still have time. And we also present you an accelerated version of the algorithm. But before that, let's see how this problem can actually arise from the do formulation of some problem. So then this means the problem is not just by design. It's not the user who divided the long vector, the huge scale optimization into small blocks, but also it arises from some do formulation of known problem. Let's consider this. Let's consider the regularized empirical risk minimization. And then I will show you the do formulation of this one. We will give you this block structure. Okay, so let's consider this regularized empirical risk minimization. This is a regularization term. So we split this matrix A in dimension d by n into n columns. So here, each block is just so we just split into columns, right? Each AI is a long vector. It's in RD, just one column. And phi 1 to phi n, they are convex function on real numbers. Here, this is just a real number, AI transpose W, because this is just a vector, right? Vector in RD. And here, G is a function on RD. That's what we have seen in augmented Lagrangian or ADMM. Whenever you see this kind of structure, you just try to decompose it, right? Because here you have AI transpose W, here is W, they're different, and then we try to decompose it. So this is a way that we introduce another variable yi representing AI transpose wi. So then this problem becomes decomposable, right? This is the common trick we always use to write a do formulation. Then we can write down the do function. Here xi is the do variable associated with each of the constraint there. Okay, so here we just derive this do function here. It's quite standard at what we have seen so far, right? We just do this reformulation, change infimum to be the soup by adding a minus sign, and then we use the conjugate function, right? And here finally we rescale this x vector. We scale x times, we multiply x by this constant n and call this new vector as u. U is in the dimension Rd. X is in Rd, yes, this is in Rd. Yes.
From first line to the second line, we have you're saying that infimum of sum is sum of infimums. Right?
Yeah, this can be interchanged.
Does it hold always infimum of sum is equal to sum of infimums?
If you have finite sum, this is of course always true.
If you have finite samples,
Finite sum, here n is finite number. There's no difference between the two. Okay, so this is the do function. Then if you maximize the do function, then it gives us the do problem. Here is not right. This is in Rn. Because here W is in Rd, Y is in Rn. Basically, that d function is here. This is a do function. D of U is here. The do problem is just to maximize the do function. And then we can, so this is equivalent to the minimization, right, by adding a minus sign here. We can put it into the composite structure we have for the randomized coordinate block descent method. So the f function is this one. F function is this lambda conjugate of g. And this h function, h is the one where we have the decomposable structure. It has a block coordinate structure, right? H is summation of hi of ui. And here, this one exactly has this decomposable structure. Phi I of ui, phi of minus ui, phi star of minus ui. Right. So here we have, we divide this. This is a special example, quite special, because we divide this vector u into just exactly n blocks. Each coordinate is a block, right? So each ni, in our notation, each ni is just 1, and b is equal to n. This is a special example. But here you can exactly see this formulation, the decomposable structure can be actually coming from a do formulation of some known problem. It's not just the user-specified structure, but also comes from real problem. Right, so this shows that usually this is called the finite sum optimization problem, because here this function has this finite sum structure. Sorry, this one has the this one. This is a finite sum structure. And this one is the block decomposable structure. So these two are due to each other. Okay. It's a nice observation.
Professor, I just have one quick question about that. So is that the same reason that, for instance, for things like empirical risk minimization, that stochastic methods work because you have that finite sum structure? And when you're doing a stochastic gradient, you're essentially kind of doing something akin to decomposable structures, just.
So yeah, this is the reason why usually you just take a sample or a batch of the components, because this n could be very large.
Right.
And then if you compute the full gradient, you are computing for all the n functions. Then it will be quite expensive in some cases. So you just take one sample or a bunch of them just to elevate the computation per iteration. And this is also the reason why this is also called empirical risk is because this is an approximation to the stochastic optimization problem, right? Originally, this would be expectation of some phi function of x. And then, because expectation is not, gradient to this expectation is not easy to evaluate, then you replace this function by its sample average approximation SAA. This is a notion in stochastic optimization. You take a few samples from the, let's make it more precise. So this is a function depending on both the decision variable and also the randomness here. So you need to minimize x under this expectation of C. And usually, because expectation means integration. Integration in high dimensional is intractable. So the common strategy is to take a few samples from this C. So we take C1 to Cn from this distribution C. Then we approximate this function by its sample average. Okay, so this is why we call this as an empirical risk. because this is just some samples. This is not the population risk. Okay. And this n could be very large. Yeah, because explicitly when n is large enough, n goes to infinity, then this approximates this function by law of large numbers. I don't think I have enough time to describe the method. The next time we will talk about the acceleration method. The one we just talked about, the randomized block coordinate descent is unaccelerated. It's an extension of the gradient method, right? We just do gradient step, but no acceleration. This method can also be accelerated to get better convergence rate. Before the class ends, I want to ask you, do you need an extension for this homework?
That would be appreciated.
You need an extension? Because some people requested an extension, but not enough number of requests. If there are more requests, I will give you an extension maybe by the end of the week, the end of Sunday.
That would be appreciated.
Yeah, then.
Okay, great. But the next homework, I will release it as well. I will release it as scheduled on Thursday because that one will be also challenging. But you will have 3 weeks to finish it, I think. So I want to give you enough time.
We don't have IPP framework anymore.
No IPP. The one you work on, the homework is the last one. That is very challenging, right?
Yeah.
And that's the last IPP. Okay, then the new deadline will be the end of Sunday for proper set 4. Yeah, I will make an announcement on the blackboard.
Yes, sir. You wrote it for me?
Yeah.
Perfect. Yeah,
Yeah, it's always good to be close with the
exactly.
Yeah.
Thank you very much.
But this is for Dr. This is this.
要从 x 和 x_q 的，我去看看它有没有能不能找一个 hint。
是吧？
是这意思吗？
是，但是下面这个，这个是 obvious 吗？这个是 obvious 吗？
因为你如果都有了，一方面是答不的，就往真死。5分钟。